All right, we have been calculating areas between curves. Now we're going to kick it up a notch and calculate volumes between those curves. And we're going to learn two methods of doing that, the disk method and the washer method. You have to kind of decide based on the graph which method that is best to use. So let's take a look at first kind of the basis of taking volumes. And again, we look at the Riemann sums where you're adding up a lot of sums of area times the third dimension, which gives you volume. And if you add up all those little subintervals of areas, you get the volume. And so what we're going to take is a cross section of a solid, find its area, and then we're going to take the Riemann sum. Now the way the Riemann sum looks, remember how we turned those into integrals, the volume equals A to B of the area between the curves, or the area between the curve and the x-axis, times the small partition of x. So there are two methods I said we were going to do. Now, what we have to imagine is, in the disk method, this little triangle is circulating around, rotating around the x-axis. So when it rotates around, it creates a circle. It actually creates a cone. And so if you slice that cone, this triangle is circulating. If you slice the cone, you get circles, which we fancifully call discs in this method. Disc circles are the same thing. So we know the area of a circle is pi r squared. So what we do is, this is the radius. This is the radius. So whatever our function is the radius of that triangle. All right, we're going to do a couple examples of disk method. The washer method, on the other hand, just like it says, creates a washer. If you rotate this top function around and then the lower function around, you would come up with a washer, and it goes around the x-axis. Okay, so you're rotating around the x-axis. This upper function is your outer washer circle. The inner function is going to be your inner washer circle. So in the washer method, if you take the area of the big circle, we'll call that R, big R, minus the radius of the small circle, squared, minus pi r squared actually. Area of one circle minus the area of the other circle. That is how you will get your area that you use in your volume equation. Okay, and you have your A and B limits of integration that you use. All right, let's do a couple examples. Well, first of all, this is how you do it. You sketch the solid and a cross section. Figure out whether it's a disc or a washer. Find the area formula, whether it's just a circle or washer for right now. There are actually other methods to use. These are the only two we're going to use in Calculus AB, just so you know. And find the limits of integration, A and B, and then integrate to get your volume. So find A and B, find the area formula, and then do it. Okay, first example is, this is actually from a video that we have, and this actually might be on your, in your book as one of the examples. So let's see, x plus 2y equals 2. So first thing we want to do is solve for y and graph this. So if we solve this equation for y, x plus 2y equals 2, we're going to subtract x from both sides, and then we're going to divide both parts by 2. So that equals 1 minus a half of an x. All right, that is our function. Now, if we graph that, that's a negative sloped function. It crosses the x-axis at 1. And let's see, it has a negative 1/2 slope, which is just a little steeper than the way I do it. Let me redraw that. Here's one steep slope. And what we want to do is take the volume of the solid generated by revolving the shaded region around the x-axis. This is your shaded region. Okay, we're going to take that from just the first quadrant and revolve it around the x-axis. So what we're going to need to find are the limits of integration, a and b, and we're also going to have to find our area formula. All right, so since we're revolving around the x-axis, this is a solid, if we revolve it down here, it is a solid circle. So this is a disk method. So our area is pi r squared, and our r is going to be our y value, because it's the height of this red line, which is our function line. So pi times 1 minus 1/2 of an x. Remember, pi is just a number squared. Don't forget squared. Pi is just a number, so don't get excited about pi's. Now, next thing we need to do is find the limits of integration. So we need to find what is x when y equals 0. So I think we can do that pretty easily from this equation. X plus 2 times 0 equals 2. Therefore, x must equal 2. So b is 2, a is 0. So we are going to take, remember, volume equals the integral a to b, which is 0 to 2, of the area function. So we're going to translate the area function down here. Now, in order to keep pi in its rightful place, we could put it in front of the antiderivative sign and then do this. All right, for many of these, we are going to be using our calculators. Now, you could do that by hand if you want, but really I want you to focus. You should know how to do those derivatives by now. Really want you to focus on the setup. Setting this up and getting this equation is our main goal here, not the answer, which happens to be 2.09. I might need another decimal place up there. 2 pi over 3. You guys can tell me later if I need another decimal place on there. Okay, so that is our first example. Next example is number 12 from your book, page 407. This one's a little more fun, only because it involves 3 functions, okay? Now, one of them is y equals 0. That's the x-axis. All right, we're going to revolve the boundaries, the region about the x-axis. Okay, y equals x cubed is a function which is a cubic. Looks like that. This is the x-axis. And x equals 2 is also a line. So let's draw x equals 2 here. All right, that makes it kind of easier, doesn't it? We know that x cubed, y equals x cubed, crosses at 0. And so we know that we're going from 0 to 2. Ooh, I like it so far. 0 to 2. The region that we are going to be revolving is this little curvy wedge. It's not a triangle. It's just a curvy wedge. We're going to rotate that around the x-axis. And the radius of that would make a disk when we rotate that around. And the area of that is going to equal pi r squared. R is going to be x cubed squared. Don't forget the squared on there. I say that because I tend to forget to put squared up there. All right, so x cubed squared is x to the, remember we multiply them, x to the 6th. All right, that should give you your lovely answer of 57.45, or that also translates as 128 pi over 7. if you were to use your calculator. Okay, I just want to make a little point here about this should really be 57.446. Remember, 3 decimal places, truncated or rounded. This answer from back here should be 2.094. Please get in the habit, big habit, of putting 3 decimal places on here. Okay, the next example is a washer. We're going to take these 2 functions and graph them. All right, so this is another example. This might also be in your book. It's from a video we have. But anyway, we're going to find the volume of the solid generated by revolving about the x-axis, the region bounded by x plus 3 and x squared plus 1. All right, so we have a line and a parabola. This is the way the graphs look. So this is the area, which is bounded. It goes from this point right here to this point over here. So those are going to be our 2 limits of integration. Now, our area is going to make a washer. All right, we are going to have an area where that red line revolves around the x-axis, which is going to make a circle. Pi big R squared. And then we're going to subtract the inside circle, which is made by revolving that portion of the parabola around the x-axis. So R, big R, is going to be x plus 3 squared, and little r is going to be x squared plus 1, because we write the line on top because it's above the parabola. All right, so we've got our area. Oops, don't forget your squared. Okay, we've got the area, and we want to take the integral of that area and get the volume. So now we have to figure out what A and B are. And again, we have to set these 2 equations equal to each other to find the limits of integration. Okay, so we've written the area equation into the volume, and we need to find our A and B. We're going to do that by what we did before, setting the 2 equations equal to each other. X plus 3 equals x squared plus 1. If you move everything to the right-hand side, subtract 3 from both sides, you get minus 2. This is x minus 2, x plus 1. And therefore, our 2 limits of integration are going to be -1 to 2. All right, if you put this into your calculator, you get 73.51 something, or 23.4 pi. And let me check that answer. Okay, so that should be 513. Close. All right, so we have one more example here with the washer method. This one is finding the volume of the solid generated by revolving the region bounded by the lines and curves. Actually, these are all 3 lines, and rotating them about the x-axis. So let's graph those and see what kind of area we get. Okay, so we've graphed these 3 lines. The blue one is y equals x. The green one, y equals 2x, a little bit steeper, and x equals 1 is a straight up and down line. So whenever you have x equals 1 like this, or x equals a number, you know you're going from 0 to 1. So we can start out our volume equation by knowing that we're going from 0 to 1, and now we have to figure out the area equation. Okay, the top graph is 2x. This is, by the way, going to be a washer method because you are not touching the x-axis down here. There's a gap in here. So when we rotate this around the x-axis, you actually have a hole in there. And therefore we take the disk on the outside, which is the green, is going to be our big R. The green is 2x, and square it. minus pi times y equals x and square it. And that is going to be our area equation. So we need to put this all together and calculate what it is. So let's put this antiderivative all together. And again, you can use your calculators. You should be able to do these antiderivatives without any problem that we have, at least the ones we have had so far. dx. And what you should get out of this is pi, or 3.141. And that is the end of our volumes with discs and washers. This concept is a little bit difficult to see, and there may be some additional resources online to show you how volumes revolving a region around an x-axis make discs or circles and washers. So you may want to use some of those extra resources as well.